So I want to show an example of an ideal gas process problem. So we'll start with the problem. It's 5 times 10 to the 22 molecules of an ideal gas occupy a sealed container. The gas undergoes a process shown in this PV diagram. The question is how much heat is transferred to or from the gas in this process. Okay, so we're given some information. We're given the number of molecules, and we're also given initial pressures and final pressures, and initial temperature and initial volume and final volume here. And we're asked to find heat. Right? How much heat is transferred to or from the gas. So I want to sketch out our approach. We're looking for Q. Right? Q equals what? Alright, we can relate Q to the first law of thermodynamics, right, where delta E thermal equals Q, or the heat, added to the system, plus the work done on the system. Or we could write this as Q minus the work done by the gas, right? Remember, the work done on the gas and the work done by the gas are the same, but they have different signs. Alright, so Q is what we're solving for. So if we could figure out the work and the change in thermal energy, then we could use the simple relationships to solve that. So the change in thermal energy is related to a change in temperature. Right? Change in thermal energy is not equal to delta T, but it's equal to delta T times some stuff that we know, actually. So we need to find delta T to find this term. And to find the work done by the gas, it's actually pretty simple. If we have a PV diagram, it's simply the area of PV curve, right? Or the area under the curve. Okay, so this is our approach. We need to find the work done by the gas by finding the area under the curve, and we need to find delta T so we can multiply it by 3/2 in K. Right, to get delta E thermal, and then we just plug it into really this relationship, right? Yeah, delta E thermal equals Q minus work done by the gas. Okay, so that's our approach. Okay, so we're given N, so maybe I'll collect some variables over here. N is 5 times 10 to the 22, right? Molecules, depending on what the gas is, right? Could be not a molecule, it could just be an atom, a single atom. And we see in this process, the arrow tells us the direction that we're going, right? So we're going from this initial point to this final point. So we can read V initial and P initial directly off of this graph. Right, so we'll say V initial is 1,000 cubic centimeters. P initial is 380 kilopascals. And it would be useful here to convert these to SI units, right? Particularly if we're going to find the area under this curve, we need the pressures and volumes to be in SI units so that the area comes out in joules. So to convert from cubic centimeters to cubic meters, we just multiply by 10 to the minus 6, right? Divide by 1,000,000. So I'm just going to leave it that way. I'm going to say 1,000 times 10 to the minus 6 cubic meters. And kilopascals to regular pascals is just a factor of 1,000. That one I'll go ahead and multiply by. Just add those zeros and we've got pascals. Okay, so V initial, P initial, we can do the same thing for V final. We can read directly off of here. It's 880 times 10 to the minus 6 cubic meters. And P final is 455,000 pascals. Okay, so let's start by finding the work done by the gas. Alright, so the work done here is simply the area under this curve. And maybe I'll do this on a separate sheet and slide this up slightly. Okay, so the work done by the gas, W gas, is the area. And if it's a straight line, we can simply say P average times delta V. Alright, you can argue that to yourself if you need to. So again, we can sketch out the area we're looking for. It's this little trapezoid. And actually that should give you enough. The area of a trapezoid is the average of the bases times the height, right? That works out to be the same expression as this. Okay, so we can just plug some numbers in for that. P average is half of the sum, right? That's how an average works. And delta V is V final minus V initial. Sorry, I should have called these initial and final here. Okay, so we can just plug these numbers in. Alright, so that's 1/2, what was P initial? 380,000 pascals plus 455,000 pascals times the difference in the volumes, and now the order here matters. This is 880 times 10 to the minus 6 cubic meters minus 1,000 times 10 to the minus 6 cubic meters. Right, and if you do all of that math, what you'll find is that the area here is 50.1 joules, and it's negative. Right, it's negative because the math told us, but we also know that it's negative because we're going left on a PV diagram, right? If the volume of the gas is decreasing, that means work is being done on it. So W gas, the work done by the gas, is going to be negative. All right. The other way to think about it is, if you're familiar with calculus and integrals, if you integrate to the left, you're going to get a negative area. Right. But I like the idea that if the gas is being compressed, the work done by it is negative, because it's not actually doing work, something's doing work on it. Alright, so that's useful. The work done by the gas is minus 50.1 joules, so we will write that here. W gas equals minus 50.1 joules. So if we go back to our scheme here, we figured this one out. Now we need to figure out delta T. Right, so how do we find delta T? Well, we need T final and T initial, right? So let's do that, I don't know, do that in blue. So delta T equals T final minus T initial. Neither of these things is given to us. Alright, but we do have the pressures, P initial and P final, we have the volumes, and we have the number of molecules. Alright, so we could use the ideal gas law to figure this out. Right? The ideal gas law says PV equals NKT. So I can do that for each point, for the initial point, for the final point. Okay, so I'll go ahead and solve it for T. T initial is going to be P initial, V initial, divided by N KB. Alright, N's not changing because it's a sealed container. So now I can just plug these numbers in. P initial was 380,000 pascals times the volume is 1,000 times 10 to the minus 6 cubic meters, all divided by 5 times 10 to the 22 times 1.38 times 10 to the minus 23, that's the Boltzmann constant, joules per Kelvin. Alright, so the numerator gives me joules. P times V, just like the area of this, is joules. And I'm dividing by joules and dividing by 1 over K. So 1 over K is just K, right, or Kelvin. So that gives me the temperature is 550.7 Kelvin. Okay, so I'll do the same thing for the second temperature, and I will do that. I'm going to just flip the paper, and we'll do that here. Alright, so T final is P final V final divided by NKB, just like I had for the other one. So I'll plug all those numbers in. That's 455,000 times 880, times 10 to the minus 6, all divided by 5 times 10 to the 22, times 1.38, times 10 to the minus 23. If you do all of that, you get 580.3 Kelvin. Okay, so we collect those two terms. Final we just found was 580.3. Initial was 550.7, which gives us a delta T of 29.6 Kelvin. So why did we need delta T? Well, we needed it to find delta E thermal, which I had in blue, so we'll use blue. Or no, I've been using blue. Okay, so yeah, we'll do that right below here. Delta E thermal, if you recall, is 3/2 in KB times delta T. Alright, so I just need to plug into that. Let's get this up just a tiny bit so we can see it. 3/2, 5 times 10 to the 22, 1.38 times 10 to the minus 23, times this 29.6 Kelvin. If you do all of that, you will find that the change in thermal energy is 30.6 joules. Alright, so we take this back to our original paper, the work done by the gas we found. Now we found the change in thermal energy was 30.6 joules, and it was positive, notice, because the temperature went up, right? The final temperature was 580, the initial temperature was 550. So again, the final question here is, what is Q? So the first law of thermodynamics, we'll take these together. The first law of thermodynamics was delta E thermal is Q minus W gas, since that's the form we have this in. So that's 30.6 joules equals Q minus negative 50.1 joules. If you cancel out this and then subtract it to the other side, what you find is that Q is negative 19.5 joules. Okay, so what really happened here? We did the math. We can plug things into equations, we can follow rules and figure this out, but it would be nice to know exactly what's happening here. So what has happened is this. Gas has been compressed, right? Maybe something's pushing on it to compress it. So the volume gets smaller, and we can see from the PV diagram the pressure gets bigger. That kind of makes sense. Also from the math, the temperature got bigger. Right, so delta E thermal is positive. But heat actually left the system, right? If Q is negative, it's dumping heat. What that means is that not all of the energy that that was put into this by work being done on it went into increasing its temperature, right? Some of it was dumped to the environment. So if you were holding this piston, or sorry, this container of gas, you would feel heat leave it, right? Not only the fact that it's getting warmer, but that heat is actually leaving the system. Okay, so that is the ideal gas process example with some usage of the first law of thermodynamics, some exploration of finding the area here, and finding really finding the temperature, right, from things we didn't know. One other thing I should mention is that I could have used in this system, because it's sealed, I could have said P initial, V initial over T initial equals P final, V final over T final. And that's useful sometimes if they don't give you an N. Alright, if I didn't know N, but I did know one of the temperatures, I could find the other temperature without having to find N. Right? And then you could find N from the ideal gas law at either of those points.